A big hello to all of you at Accra from New York City. I'm excited to talk to you about image quality in low field MRI, focusing on repeatability and artifacts. In particular, I want to thank the African chapter of the ISMRM, Jones and Godwin, for their kind invitation to present to you some of the findings at our lab. These are my disclosures. So let me start off this presentation asking a fundamental question about why we need to care about image quality at low field MRI. We reviewed the accessibility of MR scanners globally in 2018 and found that the geographies with the highest population densities had the least MR scanners. Our assessment was that this was a result of two types of barriers. The first one, the more obvious one, was the scanner, which was more expensive, required sophisticated engineering, large sighting spaces, high demands on power, and among the whole body imaging modalities, relatively slower. The not so obvious but very widely recognized now is the lack of skilled human expertise in these areas coming from diverse requirements of needing a radiologist, a physicist, a radiologic nurse, and of course the radiologist. The approach that we've taken towards this problem is to collaborate with hardware developers as a software group, and then try to automate some of these functions both at the scanner and the operation ends to augment local expertise and deliver this as a solution to underserved communities. One important feature of our thought process has been trying to find the balance between accessibility and utility, which means these accessible scanners are affordable, portable, and the ones typically at very low field. And the way we think about very low field is where coil noise typically dominates the body noise. These scanners allow imaging of underserved and new populations. However, such imaging cannot be substandard compared to the state of the art. So the key considerations would be to look at the appropriateness of use and ask two fundamental questions. Does image quality meet the requirements of this intended use? And if the answer to that is yes, then is the image quality repeatable and reproducible? So we start off by looking at some commonly used practices to measure image quality on widely available and used phantoms such as the American College of Radiology or the NIST phantom for both quantitative MR and system specifications. You could ask image quality questions in vivo specific to the application that you're intending to use it for. Measures on the engineering side, however, tend to remain signal to noise ratio, geometric accuracy, resolution, and the like. We set about studying the repeatability of the very low field MR scanner we have in our lab, which is based on the design by Tom O'Reilly and Andrew Webb. Here are some construction details of these magnet, gradient, and RF coils. It ships in a box that is 6 feet at its longest dimension, and you can see this without the safety stickers at that time put into our lab space, and you can make out how portable it is. It weighs less than 300 kilos. The scanner is shipped out from Multiwave Technologies. The other imaging related specifications of the scanner are listed in this table, and that's how our coils look like. The phantom we chose for this repeatability study includes a cylinder which is 22 centimeters mimics the American College of Radiology phantom, but with slightly smaller dimensions so that it can actually fit into our more tight dimensions of the RF coil we have. The study design involved scanning over 10 days with 3 sessions each day. Each session consisted of measuring environmental parameters such as temperature and humidity, followed by acquisition of a B0 map before and after the imaging sequence, which was the 3D TSC, which we use as a workhorse in our lab. The protocol that we had to compare as gold standard just for image quality purposes was to look at the 3T, which is the 2D turbo spin echo, not the 3D space, and the 0.05T with an ETL of 4, TRTE of 520 milliseconds. The resolution that we were after was 1.5 by 1.5 by 5 mm cubed. The protocol and processing were relatively straightforward. The reconstruction included Fourier transform inversion followed by drift correction, whereas the post-processing involved correcting for B0 inhomogeneity using standard off-resonance correction methods like the conjugate phase reconstruction. And the image analysis were picking out slices of the phantom where we would measure eccentricity, signal to noise ratio, and image uniformity. Eccentricity here is taken to be a measure of geometric accuracy. Given that the phantom was a cylinder, for the circle we would expect an eccentricity of 0, and any distortion from there would put it away from an eccentricity value of 0. Image uniformity was looked at through the computation of the standard deviation metric in a region of homogeneous signal intensity, or intended region of homogeneous signal intensity. Here is a representative data of all the slices from the 3T and the 0.05T without and with correction using the conjugate phase reconstruction. The orange arrows in A and B show the areas of geometric distortion, whereas the red arrows show the shift in the slice direction once the off-resonance correction has been accomplished. Then here's another qualitative representation of one of the slices with the most features in that phantom for 3 sessions and 10 days without and with off-resonance correction. The environmental parameters that we measured, temperature and humidity, showed a bound of between 1.5 degrees Celsius for most days. You can see the S1 for session 1, B for before, and A for after. We did have the odd day where these changed significantly, but it was pretty much on that particular day and for one particular session, which we attribute to the HVAC system in the room. Here's a very interesting finding that we have, of course, validated by previous knowledge that as you increase temperature, frequency decreases. That follows from the graph. If you can follow my arrow as you go towards the right bottom, you see that the frequency decreases. The more interesting finding is that these variations actually changed consistently based on what session we were imaging in. Session 1 always had the lowest temperature and the highest frequency, and by end of session 3, we would consistently see higher temperatures and lower frequency, which we attribute to gradient heating, although we had sufficient cooling time between these 3 sessions. We attribute that this would be based on time of day imaging, and temperature during the day would be more than during the night. So there are other publications in this direction which also look at time of day neuroimaging on 3T and how that influences some of the measures we obtain from the brain that we found to be interesting and to be cognizant of in our studies when we went in vivo. Looking at the effect of the mean um, drift in frequency and also the mean deviation in B0 before and after for these three sessions, we find that they're closely bunched when you consider the overall field drift in terms of about 2000 ppm range or 4000 hertz at this frequency, at this magnetic field strength. Um, we then looked at the variations in the main magnetic field before and after the turbo spin echo sequence, with the expectation that at this field strength, most of the changes in B0 are scanner specific and not anatomy induced. Um, However, we did see some movement of the hotspots, like you can see here, but that was not prevalent to all the days. We attribute that to environmental factors changing rather than anything specific to the anatomy that we're imaging. You would mostly expect one colored difference, meaning that there'd be a global shift just because of the temperature drift over time. On day 10, session 1, we had an unannounced visitor who opened the door and walked in. So we see a huge change there. But other than that, you will mostly see that the hotspots for B0 remain mostly consistent before and after, um, with a few variations, uh, probably on 3 out of 30 occasions. Here's what we found for the signal to noise ratio and off resonance correction computations. The signal to noise ratio was highly consistent within a range of about 5 arbitrary units, whereas in the cases of image uniformity and eccentricity, you can see the first day being different than the rest of the days. This was mostly because of the scanner being left on the first day, and from the second day onwards, they were always turned off after every session. To summarize, we found that the frequency and signal to noise ratio were highly repeatable, whereas the image uniformity and eccentricity metrics had a higher coefficient of variation because of the way that I mentioned about the first day being with the system being left on for a longer period of time. Now, we then moved in vivo to kind of identify and mitigate artifacts to improve image quality. Now, why is this necessary? So, the need for identifying artifacts comes from the way we have the workflow for our imaging setup, where once a patient is in position, you acquire the images, but these images, while they're getting scanned, you get the images are looked at by the MR technician for a quality assurance or artifact identification process. If they are all okay, then they go to the archival system. If they're not, one needs to make changes in a timely manner during acquisition, and this oftentimes requires MR physics expertise or at least working knowledge of these artifacts and their fixes. Here are a bunch of examples that I want to show you that you encounter at low field and some of the solutions we've had towards fixing those. One of the first things is to look at the effect of echo time. Our target acquisition contrast is T2 weighted imaging, and with reduced echo time, you probably can increase the echo train length at such field strengths. However, one needs to be cognizant of banding artifacts because of residual magnetization. And as you can see, if you increase the echo time to a number where this banding reduces, you then obtain images in vivo which don't have those banding artifacts. The effect of trajectory in the case of T2 weighted imaging is straightforward, where you need to have a linear traversal of the two phase encoding directions, given that this is a 3D acquisition matrix. Here you can see examples of in-out where you start from the center of k-space, and then linear old represented one of the schemes that we inherited, and linear new is something that we fixed in-house later. And this is the echo train length varying over different acquisition data sets that we have. As you can observe, more the number of echoes, you get highly T2 weighted imaging, but also at the expense of lost signal. And you need to pick the appropriate acquisition parameters such that you get the right weighting and a balance between signal to noise ratio as well. The effect of bandwidth is highly pronounced at low field. Lower bandwidth means sampling for a longer time, means you probably get more signal to noise ratio, but the effect of B0 inhomogeneity is also high, that you can observe at 20 kilohertz when you start seeing the effect of B0 resulting in geometric distortions, which is significantly corrected when you go to 40 kilohertz, but the signal to noise ratio is lesser at 40 kilohertz. The scanner that we have requires us to image off center. The center for us is 19 centimeters from the edge of the bore, but when you actually move somebody who's about 5 feet 8 or 5 feet 10, then it's about 16 centimeters from the edge of the bore, and you can see a slight drop in signal to noise ratio compared to the phantom acquisitions. And we've also shown you an example of 13 centimeters of the bore where you can start seeing some signal depositions because of off resonance correction. In summary, what we understand is that most images at low field contain artifacts. You need to understand whether it's critical or not for the question you're asking, and then you need to identify and localize these artifacts based on your acquisition parameters, and with enough system experience and expertise you can mitigate these. Identifying these artifacts requires expertise and time. These artifacts negatively affect the diagnostic quality and are sometimes confused with pathology. MR technicians with such skills are scarce in low accessibility areas. So to have a mechanism, probably using deep learning, where you can leverage this expertise on site to support the MR technician will be useful in such low field. This is the segue to the final part of this presentation, where we automated artifact detection using deep learning based on our work ranging from 0.2T all the way to 3T in different vendors. So let's revisit the slide that we saw before, which demonstrates the need for physics expertise and a working knowledge of MR artifacts during scan time to a situation where you can have deep learning assist the MR technician. We focused on 3 artifacts which were the most commonly occurring in the data set that we had, namely wraparound, Gibbs, and motion. Wraparound, despite very easy to recognize, it actually causes significant challenges if it overlaps in the region of interest. Gibbs ringing results from insufficient sampling of high frequency data in k-space, and it might be spread in multiple places in the image. For wraparound, here's our training and architecture details. We leverage the publicly available IXI dataset with 1.5T and 3T. We used a simple convolutional neural network being a binary classifier model. Our real world images came from Ibadan, Nigeria at magnetic field strengths at 0.2T, 360, and 1.5T. We use the ReLU activation and the Atom optimizer. For the in-plane wraparound, we accomplished a training accuracy of 100%, which kind of indicated overfitting. But we did try to generalize as much as possible. And as you can see from some of the next slides, where our test performance has also been 100%, it appears that in-plane wraparound is very hard to break, even with prospective data from other scanners that the model hasn't seen. The through plane artifact, however, did achieve reasonable measures for precision and recall. As you can see here, we also focused on explainability of these models to see why they did what they did and to be right for the right reasons. We used the gradient class activation maps to highlight regions that were responsible for the decision, and you can see the hotspots indicating the areas of overlap and identifying the wraparound, especially in the in-plane in the in-plane data. And you can see where the model goes wrong, also where it assumes that there is some overlap, but there is none for the false positive and the false negatives. This is the performance for the precision recall on the validation dataset, which consisted of low field data, and the test dataset, which completely consisted of low field data. The prospective studies for the wraparound, given that we were accomplishing 100% accuracy on in plane, we decided to test it on GE and Siemens 3T data that it did not see before. And these were the acquisition details, and we also looked at Gibbs ringing and motion artifacts by inducing subject motion. Here's the conventional workflow of how you would typically do an exam where, and this is all demonstrated on T1 imaging, where you would where you would acquire the whole volume, and then the technician would look at it, and if they found something to be bothersome, they would reacquire the whole data. The approach that we tried to use Artifact ID, our artifact finder tool, is to break these full volume acquisitions into segments and interleave them with Artifact ID looking at each segment, so that in case a segment failed, you would lose only time for the segment rather than redoing the whole volume. Here's a simple demonstration of that idea, where instead of looking at the whole volume, you would look at mostly a slab or a segment of the whole volume. Here are some representative data of the prospective studies, where again, with in plane we had 100% accuracy. For the through plane, we did have some false positives and false negatives, with the GradCam maps showing areas where it thought were the overlaps. Here's a quick demonstration of this idea. This is prospective while the scan is going on. You're acquiring the volume, and then at the end of it, when it passes on, you would see that Artifact ID would start assessing the first volume, and if it turned out to be off, the whole volume would have to be reacquired. So you see that with the red check mark. Now with the first segment, if the first segment alone is getting looked at for, let's say, in plane wraparound, then as it processes, then you have only 3 minutes, so instead of 5 minutes of the whole volume, and we see whether Artifact ID thinks it's erroneous. It does, so you reacquire the segment later on, but you've lost only 3 minutes instead of the total 5. So for Gibbs ringing, initially we looked at k-space because this is due to the truncation of uh, the values in k-space data. But then, uh, given that we were not able to explain this more thoroughly in the class activation maps, which should have kind of highlighted areas that uh, that actually show truncation of k-space, we then looked at the image space equivalent using a method called cutart, where you induce Gibbs ringing into images and then randomly insert those patches from the artifact prone to the normal to induce Gibbs ringing in different parts of the brain image. Um, then our localization and explainability improved, wherein we could see red dots in areas where you did have Gibbs ringing. So in this case, we were able to come up with methods where you showed explainability for um, for introducing cutart. Um, the way we actually improved on the false positive and the false negative rates was by introducing what is known as the RRR loss, or the right for the right reasons loss, which kind of um, allows the introduction of the mask into the optimization, so you can actually tell the optimizer to focus on certain areas which we know are from the cutart. I'm not sure if you can follow the Gibbs ringing shown by these red arrows, but it kind of picks up the cutart places where we've introduced it, which means, excuse me, which means that not only are we getting good confusion matrix performances, but also we are able to explain the reasons why it's getting picked. And as you can see, our accuracy and for both training and validation went up significantly once we introduced the RRR loss. And here are some representative examples for that. For motion, we started with a binary classification model where you could see the difference between motion and no motion. And we started introducing these motions using our own inbuilt simulators. Uh, we then started thinking about what's acceptable motion to then move into a multi-class classification model. The way we did this was to have a random parameter generator which looked at rotation and translation parameters, and then generated a motion curve and figured out what phase encodes these motion events would occur, and the number of motion events that you would have. Once we put this together, um, we then had the multi-class motion model with the GradCam maps. What you can see is the intensity of the GradCam maps increase with severity in motion, as you can see between the three groups of these columns here. Of course, the most challenging question is to say what is the definition of class 1 and class 2 in terms of motion. We set different bounds on the variations in rotation and translation parameters to define class 1 and class 2. In summary, artifact ID identifies and assesses artifacts in a timely manner and can be integrated inline during acquisition. Uh, we've strongly emphasized on GradCam heat maps that suggest that artifact ID models are able to recognize these three artifacts and localize them. Our ongoing work is to do a pre-deployment Mount Sinai, and of course deploy this at our collaborative site in Ibadan, and provide basic artifact mitigation suggestions as a next step. With that, I'd like to thank some of the wonderful people in my lab who've contributed to this. Dr. Pawan Pujar for the repeatability data and generating a series of examples on in vivo 0.05T data. Kunal and Shaunak on the repeatability data as well. Shravan and Marina for the artifact ID work, and we'd like to welcome Ivan from Uganda with also acknowledging support from CZI and Smarta. I'd like to thank all my wonderful collaborators from different parts of the world, as well as some of them being beta site testers. And a shout out to Tony for his wonderful work of DL denoising of these 5.05T images along with his colleagues. I'd like to thank the funding sources and you for your attention and patient hearing. Thank you.